as well. And we should be live. I'll just
Great.
check.
So I'll just wait about 2 minutes and then introduce you.
You still see the screen? I mean, the kind of frame
Yes.
vanished on my side. So.
I can see it, yeah.
Right.
All right, so I'll go ahead and introduce today's speaker. So today we have Professor Michael Zuerch from the Department of Chemistry at the University of California, Berkeley. So Michael received his PhD in 2014 from the Friedrich Schiller University in Jena. After that, he was a postdoc at Berkeley and then moved back to Germany in order to start an independent group at the Fritz Haber Institute. Michael works in linear and nonlinear XUV spectroscopy and attosecond science, and for that work he was awarded the 2021 Fresnel Prize of the European Physical Society. He's also named a Hellman Fellow and won a W.M. Keck Foundation Science and Engineering Research Award. So without further ado, I'd like to introduce Michael, and today he will be talking to us about nonlinear extreme ultraviolet spectroscopy.
Excellent. Thank you so much, Mike. Thanks for having me here. I'm really excited about this opportunity and thank the organizers to invite me for this seminar. So what I will be talking about today is mostly work that we conducted at facilities in the last about, I would say, 2.5 years. And we've been addressing some interesting new science in the area of nonlinear extreme ultraviolet spectroscopy, developing essentially a new probe to study surfaces and symmetry breaking with elemental resolution. Before I get started with the science, I first want to acknowledge all the people who did the work, and these are mainly my current and former crew members, as well as our collaborators. I want to especially shout out to Sasabot Yamnuch at UC San Diego. He's an excellent graduate student working with Todd Pascal, and he did most of the numerical simulations you will see in today's talk. So this has been a very productive collaboration the last, say, 2.5 years that we have established to develop this field, and it's mostly to his effort to do all the numerical simulations that you will see today. All right, so what we are interested in is studying complex interfaces and surfaces. So that is relevant for many, many areas. So as chemists, for example, we are interested in photocatalysis and developing new platforms for photocatalysis. So here, a complex interface could be, the interface between a catalytic site and a complex chemical environment where chemical reactions happen once light impinges and we get charge separation, say in a photoabsorber. So we're typically interested in studying what does the charge transfer process look like at these interfaces and surfaces. There's many many applications in biochemistry as well, material sciences and surface chemistry, where one would really like to know more about the physical chemistry happening at this interface, specifically charge transfers and in general chemical reactions. Other areas of interest where one really wants to understand better complex interfaces, and especially buried interfaces, are modern batteries. For example, shown here, some solid state battery with the lithium ion as lithium ions as charge carriers. So one would be, for example, interested in these interfaces between electrolyte and cathode to understand better where losses occur, things like that. Likewise, in the area of 2D materials, this is of course a very complex field that evolved in the last few years, where people looked into first exfoliating down to the 2D limit. And now in the last, say, few years, actually people start again the other way and start stacking those up in very deterministic ways and find all sorts of interesting physical behaviors as you bring different 2D materials and van der Waals materials into contact, and people dream of creating very new physical systems that have very, very defined properties around ferroelectricity, magnetism. Also here at Berkeley, we're thinking about actually chemistry in van der Waals gaps and within 2D materials and things like that. So there's a lot of interest in studying interfaces in complex environments. And so what we're typically interested in studying in this context is, for example, properties like the potential, the structure of the surface. We want to study charge transfer dynamics. And in case of 2D materials and emerging properties, especially at the interfaces of different materials, we're interested in correlations that emerge between different entities of the systems. And so that these examples show us at the same time that we have a large chemical or say atomistic complexity in those systems. Yeah, we have multiple different atomic species in interacting with one another, and the complex interplay is what gives the interface its function. And so what we set out to do is trying to develop methods to better understand interfaces from an atomic perspective, and to better understand what are the contributions of an individual atomic species to the function as that emerges from such interfaces. So one method that has been used now for probably more than 40 years to study surfaces and interfaces is nonlinear spectroscopy. So that's been done in the optical and infrared regime, like I think since the late 80s, early 90s. Actually developed here at Berkeley, primarily by Ron Chen. In 1989, his famous Nature paper come out where he first described second harmonic spectroscopy. So what is nonlinear spectroscopy really? Well, a very brief introduction to that area is that, well, if we have a light pulse described by its electric field interacting with a medium, we can model the polarization response of the electrons in that material by this power series, where basically we can develop the polarization by different orders of the electric field. And in nonlinear optics, we know that this gives rise to a generation of new frequencies, like one prominent example, a second harmonic generation, where the second order term causes oscillation of the emerging electric field at twice the frequency of the incoming electric field. Other such second order processes involve, for example, some frequency generation. And so the reason this is interesting for studying surfaces and interfaces, as shown, for example, here in this example of studying phenol at an air-water interface, is because that this chi2 tensor, that's a rank 3 tensor that links the polarization with the second order of the electric field, is in fact 0 in an inversion symmetric media. So all the tensor elements are 0 if there is inversion symmetry. Therefore, we can use second harmonic generation, or for that matter, any of these second order responses, as a very sensitive probe to inversion symmetry, yeah, or actually probe inversion symmetry, I should say. This is how these methods got really interesting to study chemistry at surfaces, especially water-air surfaces with molecules at the interface here. So this has been like one of the key drivers in that field, using optical and mid-infrared pulses to study properties of molecules at water-air interfaces, for example, using this property that only at the interface where the symmetry is broken, these nonlinear components arise. So this is actually really the only optical spectroscopy with photon in and photon out that really can selectively probe one atomic layer. And so this has been around for a while, all of course driven by, and I should also say that these terms are actually quite small in magnitude as compared to the linear response of a medium. So this is why one actually needs very intense or very strong electric fields, hence requiring lasers to observe these second order nonlinear responses. So, however, with the birth of the laser and finding of second harmonic and then development of second harmonic spectroscopy, this has become a really important tool in surface chemistry. But now one caveat here is that one can study the properties of a molecule, say the orientation and some of the chemical properties. However, one does not necessarily get information about specific elements or specific contributions to the signal because one really probes the valence states. So how can we understand that? So we just think in a very simple picture about two species, atomic species A and B. We know that we have some certain valence electronic states of A and B. We know that we have typically also some core states of A and B. So these are more tightly bound electrons and the systems A and B. If we now mix those together and form a compound material consisting of A and B, say going from atoms to solids, we know there's two things happening. The one thing is that we form bands as we go from individual atoms to, say, a crystal. So we form continuous bands in the valence states. And the other thing we know is that we hybridize. So there is a mixing happening between the wave functions of A and B, resulting in a mixed state valence and conduction bands. So that's what we typically refer to as hybridization. On the other hand, the core states, they're typically energetically so separate that they don't hybridize. They are not typically mixing. They stay separate if we bring this, emerge in a combined system. I should say that's not, of course, just forming a crystal out of two atoms. Can be n atoms, and it can also be, of course, an interface with a liquid-solid interface. And all these interfaces, these hybridization effects, of course, take place, where we end up with energetic structure as exemplified here in this case. And those of you who are familiar with X-ray absorption spectroscopy or X-ray methods, you know that this is one of the key aspects that in X-ray spectroscopy we like to use to do element-specific studies, is to use one of these core electron resonances to probe transitions into these valence states. Say, if you do X-ray absorption spectroscopy, you probe the transition of a core electron from a certain element with a resonant transition into, say, empty conduction bands, giving rise to an absorption edge. So this is what we typically do in X-ray absorption spectroscopy to study specific properties of one element in a complex system. So now what we set out to do now is to investigate whether or not it is actually now possible to do this. So whether we can do actually second harmonic spectroscopy with core electrons. And so that is what a simplistic version of an energy diagram can look like. So can we use, instead of a linear X-ray absorption spectroscopy, one would use one photon to transition resonantly between a core and the valence state. Can we instead use, for example, photons of half the energy, trigger a resonant transition to a valence state, observe the second harmonic of the signal, basically adopting second harmonic spectroscopy from the visible mid-infrared to X-rays. If we can do this, we have several advantages that come from that. So one is that we are element specific, so we can isolate, or we automatically, by means of selecting this transition energy properly, we can select the response of one and only one element in a very complex setting, say with a complex liquid, complex molecules around, say, a condensed phase system at interface, and can still study, say, the response and charge transfer, say, as seen and as perceived from one specific element in the system. The other thing that comes with using X-rays is that we have large penetration depth. So we can typically shine X-rays through like stacks of material I mean, there is absorption usually, but depending on the photon energy range used, it can be quite low. So that is quite different to, for instance, photo emission techniques that can probe surfaces, but only in very clean environments when you have basically a ultra high vacuum solid interface. Here in this case, due to the large penetration depth, you actually get access to buried structures. And so the other thing is, of course, then symmetry breaking. So we can study if we can do these measurements, we can actually measure symmetry probing states, so that can be the surface buried interface, but also systems that have inherently a probe inversion symmetry. And I will show you a few examples along today's presentation where we achieved some of these properties and actually did measurements in physical systems. So if we can combine this, what we would get is an element-specific probe for surfaces, interfaces, and in general anisotropies that give rise to properties like magnetism, ferroelectricity, and such things. So that is why we're generally interested in developing these methods. So the one caveat, though, is, as I mentioned before, these nonlinear processes are highly inefficient. So they require very intense light sources. So in the visible light, we have, of course, lasers available since a number of decades, but in the X-rays, this has been not the case for a long time. But with the advent of X-ray free electron lasers, we now actually have light sources that we can use for this, for these kind of investigations. I should also point out that there is two different schemes I will talk about today in this presentation that we applied in different types of materials. So that is just by means of choosing the say photon energy of the light source that we use for our measurements. So this is always a type of resonance enhanced SHG. So and we always have to create sort of a resonance condition to take advantage from real existing states to cycle the electron through to actually observe second harmonic. So there's one possibility to basically go what we typically like to call half resonance. So we basically use photons that have half the energy of the resonance from a core state to an empty conduction band state. Or we can also go the other way where we use, oh, it's actually not nicely drawn here, but one should be up here. We use one photon to go resonant to a conduction state and then cycle through a virtual state at much higher energy and can observe second harmonic from these states. So in this case, you would observe the second harmonic in twice the energy of the X-ray linear X-ray absorption edge. And we have successfully, and I will show you examples, we have successfully measured in both of these situations. I just wanted to bring this up early so that you're all aware of the different energy schemes and why certain free electron laser energies I will show later in the talk we use in certain circumstances. So this gives us a little bit leverage also to plan the experiments and use different selection rules, for example, to excite and measure different symmetry states in the system. Okay, so now I already alluded to it that we need very intense light sources. So free electron lasers are one of the primary sources for attempting this kind of research. And indeed, the first observation of soft X-ray second harmonic generation as signals as an interfacial probe was managed just a few years ago, 2018, at the Fermi free electron laser. And so in this very first experiment in the field, people focused on a graphite crystal. They went resonant with the 1s state of carbon to the conduction band and observed the second harmonic at twice the energy. So this would refer to this scheme 2 I showed here earlier. And then essentially the way these measurements work, and this was again the first work in this field, is what you do is you essentially vary the pulse energy of your impinging free electron laser, and you measure with a spectrometer the signal at twice the frequency. And then what you typically first do is you look at the second order response. So basically you're counting the second harmonic photons depending on the pulse energy of each individual laser pulse impinging on the target. And the first thing that assures you that you actually look at a second order process is that you see this quadratic response here nicely. And so that is the first indication you have, yes, indeed, that's a second harmonic generation on that system. So that is great. So now what is the actual observable? What are we interested in measuring? Well, if we look back at the math, what we have is basically we measure an intensity at twice the frequency, say 2 omega of our impinging electric field, and that's proportional to the square of the incoming intensity, and it is proportional to this chi2 tensor. So that's the dielectric second order susceptibility, and that's, like I said, a rank 3 tensor. So this is actually what we want to know. So this is actually this tensor, these tensor elements, this is actually what contains information about the dielectric environment. This contains information about what is, say, the dielectric environment of a certain atom, say, at the surface And then, of course, from this, we can draw a conclusion like, what does it mean, though, say, if a molecule approaches and there's a charge transfer happening? That is when these properties will change, say, suppose if we can do a dynamic measurement. Yeah. So what we really want to know in these measurements and these experiments is we want to actually extract this term, right? So that's the actual observable. That's what we were interested in. So to get that, we have to do these kind of measurements, perform this quadratic fit, and then actually this constant, this fit constant, is giving us the projection of this tensor, of certain tensor elements. I will talk about these geometric aspects in a short while, and give some more details how we can understand these projections, because of course in this case when you fit, all you get is a scalar, whereas I just said that this is a rank 3 tensor. So we'll touch on the geometry aspects in a few minutes. What I want to point out here in this first work, and that's what really back then caught my imagination, what would be possible with this method, is that what you can see here is the second harmonic measured, or the second harmonic response measured for different thicknesses of this graphite film. So the researchers in this work use 100 nanometers up to 700 nanometer thin films of graphite. And well, what they see is that for all the different thicknesses, the response remains the same. And so what this tells us is that indeed this is a surface sensitive measurement. It doesn't matter how thick your crystal is, you see the same response, because all you get is essentially the surface response of the system. So that was the first reassurance that indeed when you do second harmonics, first of all, you can do second harmonic spectroscopy in the XUV, and indeed you get access to the surface. This work was also accompanied with some pretty complex DFT calculations that also confirmed these observations. So this was what really got me excited and started in this field, and that's how we got started in my group to conduct our own experiments and contribute to that field. So one caveat with this very first work is that at the time the researchers were able to collect 3 photon energies, so 3 data points across the absorption edge, and they could see that there are some non-resonant and resonant effects is what they call. So they basically said, okay, whether or not you're in resonance, if you're not in resonance with the edge, then you don't see much second harmonic. If you're above the edge with your 2 photon absorption process or with your second harmonic process, then you get an enhancement of the signal that's expected. But such spectra, of course, at this detail will not allow you to model much of the material response really and understand much of the material properties, but it was still a pioneering work that started this whole field. So what we then set out to do is then to think about how can we turn this into a spectroscopy, like how can we get much more data points, how can we get data that we can really use to infer properties of materials. And so that is where I would like to take a few moments to talk a little bit about free electron lasers per se. So let's play this again. So we did a number of experiments now at this facility here. That's the free electron laser SAKLA in Japan. And so one thing one has to know about these free electron lasers is about their function and the way those work for those of you who are not in that field. So essentially a free electron laser is first of all an electron gun where electrons get emitted from a tip, then they get accelerated to near relativistic energies, and then they are sent into a so-called undulator, which is a chain of magnets shown here in yellow and green with opposite polarity. And then due to the Lorentz force, the electrons are forced into one of such a quiver motion, and accelerated electrons emit radiation. So that is how, if the energy, the kinetic energy of the electrons and the say magnetic field, the periodicity of this alternating magnetic fields are set correctly, you can make this radiate in X-ray photon energies. And so what makes a free electron laser, however, is that these so-called undulators, so these chains of magnets are actually fairly long. So there's like several dozens of those magnets that the electrons are shot through. And now what happens is that you get an enhancement effect. We call this bunching. So there is a micro bunching effect where the emerging electric field from the X-rays acts back on the electrons. So starting from some pseudo-random emissions, so very weak random X-ray emissions, the electric field acts back on the electrons, starts to bunch them, and this gives sort of an amplification effect. I don't want to spend too much time talking about free electron laser physics, really, since we really use it as a source. But what is important to understand is that you get very strong X-rays at the end of the undulator. So there's this kind of, it's also called the self-seeding effect in a way. So you generate very little X-rays at the beginning. And then out of this initial noise from this initial measurement, from this initial emission, you get self-seeding, which then gives rise to a very strong amplification of the X-rays along passing through the undulator. And this gives rise to millijoule class or multi-millijoule class X-rays. Yeah? And so the one thing now relevant for our work is that this also called self-amplified spontaneous emission SASE effect, that's of course also known from optical lasers from back in the day, that in this case, this self-seeding or this amplification starts from noise. So every free electron laser shot in such a SASE free electron laser has sort of a slightly different spectrum, slightly different amplitude. So these pulse, these lasers are not like visible light lasers that we are usually accustomed to, that every pulse is almost identical, very constant, very low fluctuations. Those FELs, they actually chitter around in photon energy and amplitude. And here I just will replay it again. What you see, these are actually individual FEL shots of this free electron laser at a nominal center photon energy of around 30 electron volts. So you can see it jitters in energy, it jitters in amplitude, okay? And then if you want to do a spectroscopy experiment, what you do is you would typically then, by means of changing the undulator period, the undulator spacing, you can essentially then tune the central photon energy to different energies. You typically request that to the facility operators, and they will change the central photon energies, and then you illuminate your sample with a number of spots. So now, to do these experiments, of course, what seems like a bug, and a lot of free electron laser users don't like these fluctuations, but have to work around and say, in some experiments, they will just take the very clean shots for certain types of physics that people want to study. In this case, it's actually an advantage, because what we need for our measurements is anyway different pulse intensities or pulse energies at the input side of the experiment that impinge on the target. So essentially, the fluctuations we get by amplitude, automatically we can detect every single shot. So we automatically sample along this curve. So the measurement becomes a matter of statistics. Yeah, and that is actually great. So a bug becomes a feature in this case, and we can essentially directly create such a curve just by collecting data for a while. So we use the shot-to-shot intensity variations to actually map out pulse energy over roughly, a factor of 2, 3, 4, up to an order of magnitude, to actually get a very nice fit of for Chi2 extraction. And that was what was done in this first reported experiment. So then when we joined these type of experiments, what we then realized as well, it's not just the amplitude fluctuation, but what I just showed as well is we also have photon energy variation. So actually it's the FEL fluctuates in 2 dimensions, right? It fluctuates in photon energy and amplitude. So what you can actually do, if you collect even more statistics, you can now go and sub-bin each shot by its central energy and then by its amplitude. And if you collect much, much more laser shots, you actually can use that to subsample your spectrum. And that is what we then did in our first experiment on lithium niobate. We basically used a much higher number of FEL shots to kind of subsample the spectrum, first of all, to the bunches, to bandwidths in the range of a few hundred milli-electron volt per bin, and then use fine-grained tuning of the FEL to actually scan across a whole spectral range. And so that was our first work that we did in this area, where we studied lithium niobate. So just for the energetics, we use in this case the FEL tuned to 29 electron volts. So we go resonant with 2 photons to the lithium K edge in this case, in this material. And this is the measured and calculated second harmonic spectrum. With second harmonic spectrum, what I actually really mean is the Chi2 depending on photon energy. And what you can see here are certain resonances. And now we can see, compared to the first observations, actually you see there is very large richness in these spectra. And each of these humps and each of these features usually means a certain, oscillator strength in a specific symmetry broken state. The other thing we found in this work, that we're actually near a niobium edge. So we also saw other resonances that pertain to niobium 4p states. So in this case, due to this very highly spectrally resolved measurements that we were able to do by establishing this new method, we were able to now get spectra with high spectral quality that allow us to even identify different elements of the system and their individual second harmonic response. So with this first work, where we also realized lithium is actually a nice target material at the K-edge to study, specifically with the free electron laser in Japan that outputs quite a high photon yield at, say, in this XUV range. We set out then to study the next system that we were interested in more from a physics perspective, and that is lithium-osmate. So lithium-osmate, shown here in the unit cell, is a ferroelectric-like material, but it's also metallic. And so that makes it quite interesting. It's also called a polar metal. So it's in its core, it's a metal, but at the same time, it has a permanent dipole moment once it undergoes a phase transition here around 150 Kelvin. And so that makes this a kind of interesting material because these are actually contradicting properties, right? If you have ferroelectricity comes from local dipoles in each unit cell that start to form long-range order. So you have a long-range order of electric dipoles. However, if you have a metal, you would think that free electrons would roam around and start to screen those dipoles. So there should be no long-range order, really. So this was thought of being contradicting properties. However, for certain types of unit cells, and if you have a second order phase transition like that, Anderson and Blunt already in 1965 predicted that these two properties can coexist in one material. Okay, it took more than almost 50 years until 2013 when somebody actually was able to synthesize this crystal. So this was like 50 years in the making from the theoretical prediction of this phenomenon until actually someone was able to make a crystal and confirm the properties. Okay, if we look at the unit cell of lithium-osmate, so what we have is we have the oxygen coordinated octahedrons of osmium, and we have the lithium, which is in the polar phase displaced along a polar axis that spans along the c-axis of the crystal, basically in the direction of the where the polar axis points between the lithium atoms in that unit cell. And at the same time, so basically it was confirmed that this is indeed ferroelectric in its low temperature state. At the same time, one looked at the density of states of those systems, confirming that indeed it's metallic here. There is a non-zero electron density around the Fermi level, and it was confirmed that charge density, or electron density, basically stems from the osmium atoms. So in a way, one can think of the system as that osmium contributes the metallic behavior, and the displacement of lithium contributes the ferroelectric portion of the system. And the special configuration of the unit cell allows the dipoles to interact with each other and create long-range order. Okay, so what we were now interested in doing is to actually start to measure this polar phase specific to lithium, because that's what we are good at with our method. Yeah, the reason is why has this not been studied much before with other methods? Well, lithium is a very low atomic number 3, and then you have osmium, which has a very high atomic number. So if you think about doing scattering experiments with electrons or X-rays in those systems, you actually have a problem in that the scattering cross-section scales with the square of the atomic number. So you actually have a very hard time seeing very lightweight lithium in these systems. Your system is, whatever you measure in a scattering experiment, aside of neutron scattering, is going to be mostly osmium, and it's hard to detect anything from the lithium. So we basically took the approach now to say, can we do second harmonic spectroscopy resonant with lithium to actually learn something about the dielectric environment, with the idea, of course, that in the polar phase, the symmetry is broken, so we expect second harmonic emission. And then the other thing is that what I said before, that this Chi2 term, this nonlinear susceptibility, is actually a tensor where ijk, you can think of it like coordinates, like x, y, z. So basically, what this means is that there is some directional dependence in this tensor. So with the tensor elements give us basically different directions in the crystal, if you will. So if you measure this Chi2 tensor specific to lithium, you get information about the dielectric environment as seen by the lithium atoms within the system. Okay, so this was the motivation for our measurements on this system. And sure enough, we went ahead and went to SACLA with a lithium-osmate crystal. These are the energetics. We went in resonance to the valence states from the lithium 1s state with 2 photons and observed the second harmonic then at energies of the lithium KH. This is what, say, a sketch of the experiment looks like. So we operate typically in reflectivity. So the lithium-osmate crystal sits on a cryostat so that we can force it through its phase transition. And then we typically have a spectrometer that allows us to measure simultaneously the fundamental FEL in the second harmonic so that we can nicely then correlate the I of omega versus the I of 2 omega, right, with the high fidelity. And so just as an example, what one of the raw spectra looks like that we typically measure. So we have the fundamental FEL here at about 30 electron volts, and then here the second harmonic amplified by a factor of 10. Here in this graph at about 61 electron volts. So yeah, so you all see these signals are definitely discernible. We can easily measure them and then conduct essentially these energy and pulse fluctuation dependent measurements to extract the nonlinear response depending on its frequency. So now let's look a little bit at the calculations and then the data. So what do we really learn from this? So the first thing I want to show here now is number of numerical simulations. So our collaborators set out to first say, okay, well, first thing we were wondering, like, what does the second harmonic spectrum look like? So if we measure the spectrum, like, how can we infer some quantity, like the amount of lithium displacement, or actually quantify, say, the geometry in the system? So our collaborators went out and set out and said, okay, let's do some calculations first and see for different lithium displacements how much change of the second harmonic spectrum can we expect, and also what would the shape roughly look like. Okay, so what I show here now in the next few slides is that we have here our calculated second harmonic spectrum. We have here a picture of the unit cell, and basically what I show now is basically slowly displacing the lithium atom along this polar bond while I keep plotting basically the second harmonic spectrum. So the first thing, if we have very small displacement, we have the lithium almost at symmetry. I think the first calculation here is just a displacement of 0.1 angstrom or something like that. So almost center symmetry, right? In this case, we expect next to no second harmonic within, say, the numerical noise, so to say. Then if we start displacing the lithium along the bond, and each of those steps is about 0.1 angstrom, we see that the more we displace, the more second harmonic we get. And specifically now that we're at, say, 0.7 angstrom displacement of the lithium atom along this bond, we can see actually substantial enhancement here of second harmonic spectrum around the lithium KH. Yeah? So this also confirms that we really have this element selectivity. Yeah? This is like the lithium KH is round about 59, 57 electron volt for atomic lithium. So we can really see these resonance enhancements. So that gave us confidence that we can actually measure this and use it, use the relative strength of the second harmonic as a sort of quantifying this displacement of the lithium atoms. Okay, and so now this is the data that we measured on top of that. You can see, well, it's noisy, you know, so these measurements are challenging. The photon flux overall is not very high, and you have to collect lots of shots and then correlate them. But as one of the first works where we really had this highly spectrally resolved spectra, we are still quite happy with the results, since we, first of all, can replicate the general features that far away from the edge, we have like basically almost no second harmonic, and then we see these several humps here coming from different conduction band states in lithium, and especially here around the lithium KH, we get a maximizing of the second harmonic response. And indeed, our measurement here, these data points in comparison to the theory, allow us to clamp the actual observed displacement of lithium in the system to somewhere between 0.45 and 0.55 angstroms. And this is quite nice because the system has the other say number we had from literatures was done with neutron scattering. This neutron scattering, I think they observe 0.5 angstroms. So we are spot on with our estimate of the lithium displacement. But now this is done with X-rays, with femtosecond X-rays. So we can now in the future think about doing this with time-resolved characteristics that do time-resolved measurements is something you cannot do with neutron scattering. Plus X-rays are generally much more accessible than neutron sources. So that was very nice first result. But now we got to think a little bit more about what do we actually measure here. And I keep writing Chi2 effective, and I kept mentioning before this is actually a tensor. So this is something that links different directions in the crystal with different polarization directions and different, say, polarizations of the electric field. And so there is something about directionality in here. And what we measure is something effective, because really at each photon energy, it's a scalar we extract. And so just showing now the best fit to our data, let's think about what does this really mean. So if we have a rank 3 tensor, so we have tensor elements I, J, K, we can think of those as X, Y, Z really in the crystal plane. The way you think of this now is that the tensor elements I, they are, this coordinate is basically the polarization of the SHG, and then you have the polarization of the two electric fields that cause the second harmonic are then J and K. So that's how you can think of it. So you think of it like you have two electric fields corresponding to J and K that drive the system, and then the second harmonic response, the second order response would be I, right? So this is how we can think of these designation of the tensor elements. Now, one thing we can do is if we have our crystal clamped on our cryostat, we know, of course, what the orientation of the crystal is. We know what the crystal cut is. We know what the crystal planes are. We also know what the polarization of our FEL actually is. We know our FEL is p-polarized. So we know that both of the electric fields that cause the second harmonic are in plane, yeah? And the polarization of the SHG is what we don't really know in this case, but we can assume, okay, it's perpendicular or parallel, one of the two, but it doesn't matter for this kind of interpretation. But what we know is basically the whole geometry. We know the geometry of these driving fields. And now we know the geometry of our crystal, and we know for this specific unit cell, for this crystal type, we have 4 independent tensor elements in this Chi2 tensor. So these are specifically the Chi-CCC, Chi-CXX, XXC, and XXY. So these are the 4 independent tensor elements in that system. And what we showed in our work is that you can actually now, if you know how your crystal is oriented, you know what the electric field of your laser is, you can actually do all the tensor rotations and projection operations and actually determine how do these different tensor elements project into your measurement. So what do you actually measure? So what you measure is a combination of these 4 tensor elements weighted by these factors. And you can actually analytically calculate this by rotating the, say, the crystal plane and rotating the tensor elements. So applying some tensor math, you can actually analytically arrive at this result. And this is now for our specific measurement that we did. This shows you multiple things. First of all, this is quite complex. So you have to think about very carefully if you want to measure a certain response of the system in a certain crystal direction, you need to very carefully think about how to orient your crystal with respect to your electric fields. That's one thing you have to do. The other thing you have to do is if you actually orient it so that you get a projection, you have to think about how can you disentangle it. But that's the good news now, though, is that once you know what the projection is, even though you measure an effective Chi2, you can still at least learn something about to which components are you most sensitive, and get an idea of like how these different components contribute to actually observed spectrum. Okay. I should also point out how this relates to theory. If you actually do time-dependent DFT to calculate the second harmonic spectrum, and that's also another point as to why the fit may not be exactly perfect, because we know the orientation of our crystal down to 2 degrees, 3 degrees, maybe 5 degrees, something like that. We know the polarization plane of the FEL to a few degrees. So this is basically just assuming, you know, exactly the angles that we assume, but you know, we don't know 100% for sure. Then what you get from the theory collaborators, they actually calculate these tensor limits. That's all they can do. They basically run a TFT and calculate the second order response. They calculate the different tensor components, and then this green curve is actually coming from plugging these tensor components for each frequency into this analytic formula to calculate the projected response. So some of the error can stem from misalignment of our crystal, for example, that we measured a slightly different plane, a slightly different projection. So this is what makes these experiments and planning of these experiments quite complicated. I just want to show that here now for a few selected cases. What you see here now is the numerical simulations for Chi2 for these 4 independent Chi2 tensor elements for different lithium displacements. Lithium displacement now is mapped here in the color map from light green to dark green, from 0.1 angstrom to 0.8 angstroms. And you can basically now go ahead and at least trying to get some qualitative insight what does this really mean. And I wanted to show just 2 examples. So if we now look at these calculated Chi2 spectra, and here what I show is now the projection of the crystal and its charge density into the CX plane. Okay, so this is the CX plane of the crystal. And just for orientation, I marked the different atoms in here. So osmium in the center. For the polar phase, we see lithium is slightly displaced with respect to the center here. So we have a polar phase. So now we can basically look, for example, at what does chi CCC really mean in this case. Well, if this is the C-axis, what this means is that we have 2 electric fields, so 2 electric field components of the driving field and the polarization in the same direction. So basically, all the polarization pointing along the polar axis. In this case, we see the second harmonic is absolutely maximized because we are basically probing along the direction of this polar axis. Yeah. In contrast, if you look, for instance, at the tensor component x, x, y, what does it mean? Well, a projection of the electric field along x, a projection along the second electric field on y, and the polarization projected along x. Yeah, so this is what this tensor component encodes. So you see, in this case, the crystal actually looks almost centrosymmetric. There's just very little asymmetry in this direction, right? So this is what you then see here is that the second harmonic response is actually fairly weak as compared to the other component. This is just to illustrate that with proper planning, you can actually maximize the signal. You can actually select a certain direction that you probe. In our experiment, we had a combination of all 4 measured, simply the way the crystal was oriented and rotated. And I will admit, when we did the experiments, we did first not pay so much attention to it. So we just basically found this all out in the post-analysis that we have to very carefully understand the geometry of the crystal and these projections. But any case, this shows the possibilities that one has with this type of spectroscopy. Okay, now in the last few minutes, I want to touch on a few more results that we achieved using with this type of nonlinear spectroscopy. So basically, this case of lithium-osmate is a measurement on a system that is inherently symmetry broken, where we basically try to understand the anisotropies that cause this polar metal behavior in the system. Another system we studied is a buried surface, buried interface, I should say. In this experiment, we looked at the interface of boron and parylene. So the experiment was done that was done at Fermi, again, Italy. So we basically have parylene on boron. We come in with the FEL, we go resonant, and see now this is the other kind of energy scheme you can do. We go resonant with the FEL from boron 1s to a valence state, go through virtual state, and we basically observe second harmonic at twice the photon energy at 379 eV. And the way one thinks now of this experiment is that the FEL impinges. Parylene is not going to do much, it's largely transparent, it's a very thin layer. The FEL then impinges on the boron-parylene interface, generates second harmonic at this interface where the symmetry is broken. Then boron absorbs quite a bit since we are resonant with the 1s state. So basically the absorption of boron reduces the intensity sufficiently that on this second interface, boron to vacuum, we don't expect much second harmonic to be added. You basically absorb a large percentage of your incoming FEL beam within the boron slab. This is another example how you can arrange the geometry of these experiments to study specific interfaces, just as an example. And what we basically did is we compared the Planck boron vacuum interface as compared to the boron parylene interface. And what you can see in the data is that in the case of In the case of the parallel on boron, we see a shift of the spectrum as compared to vacuum by round about 2 electron volts. So we see a slight shift of the spectrum and the second harmonic response of the system. And by doing simulations, we were actually then confirming that indeed that this was expected. So if you basically have the organic on top of the boron, what happens is you get a slight charge displacement. So there's a certain charge displacement across the interface from boron. You can think of it that the parallel takes on a little bit of the charge cloud from the boron, and that causes essentially the states at the edge to shift such that you get a slightly different transition energy for boron at the interface. And that's what you effectively prove with the second harmonic. So if you would measure the XAS, and we showed in our paper, if you measure the XAS spectrum of those systems, you see absolutely no difference between a boron vacuum versus boron with parallel, because you basically measure bulk. But if you measure second harmonic, you actually see a spectral shift. And the simulations confirm it. And one thing one can do now in these kind of measurements is that you can actually simulate for different interfacial spacings, like what is actually the bond lengths from boron to this parallel, like, or to this organic, like what's the bond lengths at the interface? If you actually bring it closer together, the simulations predict that the spectrum shifts even to lower energies, whereas it shifts to higher energies if the bond is elongated. So in other words, you get actually a way how you can intrinsically measure these interfacial bond geometries without actually cutting it apart. So you can measure those in situ, and maybe in the future even dynamically when you think about charge transfers and photoexcitation events and things like that. One other thing I should point out for this work is that the simulations, we had sort of to make a compromise. So the simulations are actually done with an ethane molecule. So the simulations are done such that there's an ethane molecule approaching a boron surface. That's how the calculations were done. Yeah, parallel was a way too big molecule to simulate in those sense. So this is also already an example where we hit basically the frontier of what is possible for time-dependent TFT to calculate with supercomputers. So we had to make a compromise and basically do an estimate with a small molecule essentially approaching a surface to kind of estimate at least what is the response, right? This is why, you know, we sort of got a boron organic separation in the range of 2 angstroms, but you know, I would say the certainty, I mean, we are pretty certain that's what we see, that's where the shift comes from. But, you know, as far as exact quantification for the parallel, I would say a little bit careful here, because what we actually calculated is a molecule approaching. So one has to see the difference. But I would also like to point out that is state of the art. So that's what's possible also with numerical methods. So this also is to illustrate that our work developing the second harmonic spectroscopy for certain applications in physical chemistry and material science in combination with theory are both areas of active development where we trying to improve and push the envelope. One more example I want to show that we recently completed, submitted as a paper and should come out soon, is we measured the surface of an ion conductor. So we again went back and thought, okay, what can we do with our capability of measuring lithium so nicely? So we looked at a solid state electrolyte, lithium lanthanum titanium oxide, or short LLTO. LLTO is an ion conductor. It's one of the candidate materials for solid state, all solid state batteries, where LLTO would be the electrolyte. So you combine it with a cathode and you have a solid state battery. The LLTO is known to have a very high ionic conductivity. So basically the ions, they hop within these LTO cages. Yeah? And so what we were interested in studying now with XUV SHG in comparison to X-ray absorption spectroscopy is like, what can we learn at about the surface, at lithium at the surface of this electrolyte as a first step towards measuring like an inoperant battery down the road, possibly. Yeah. So this is the general idea. Is what we actually want to study is this electrolyte in contact with an electrode to study like what is the lithium mobility at the interface, at the buried interface. As a first step, we set out and said, okay, let's measure the surface first to see what we can see and how we can interpret it. So the experiments here again were done at SAKWA in Japan. So we went again resonant with the lithium K-edge, just with 2 XUV photons of half the energy of the K-edge transition for lithium. And this is what we observed, this is the measurement, and now this is comparing bulk and surface measurement. So the XAS bulk measurements were done here at the Advanced Light Source at Berkeley on the same sample. So what we see is nicely the lithium K edge, basically. That is what you find in many textbooks. Essentially, that's the lithium K edge. We can also use our DFT methods to at least predict and estimate the shape of this edge. So that is essentially the bulk response of the system. And now the interesting thing is that we can compare this to second harmonic generation. So that these measurements were done at the free electron laser on this very same sample. So now what you see here is that now, first of all, it looks quite different. So that's good because, you know, there's an expectation that there should be a change between bulk and surface. So what we see now is basically a structure with two humps. We see some energetic shift of the main absorption of the main resonance here. The other thing is our theory got better in the last year or two. So we now actually can very nicely predict the second harmonic response of the system as well. And we can now basically analyze these shifts. So there's one thing one has to note. This is a two-photon absorption or two-photon resonant process. So we have to think about selection rules as compared to XAS. So there's a one photon transition. This is two photons. So there's apparently different selection rules in place. So after thinking carefully about those, we still find that there's a residual shift of a few hundred milli-electron volt that we cannot explain by simply looking at the selection rules. And what we then found out once we dug deeper into this topic is that actually what we see is that at the surface of this material, the certain low frequency phonon modes are actually inhibited. So what you see here now is the calculated vibrational density of states, or you could call it also the phonon spectrum at the surface because compared to bulk for LLTO. And specifically here at this low energy region, we see that certain modes are strongly suppressed. These are the actual modes here illustrated by these like little cartoons. So these are the actual lattice modes for C, D, E, and F. Those are the ones that are basically strongly suppressed in case of the surface. And what we then found out is that this gives rise to a reduced lithium hopping. So actually what this means is from the X-ray excivis measurement, we got the input to say, okay, there is something different here, which pertains actually to shifts are then commensurate with a shift in the photon or like reduced photon spectrum. And then in turn, this allows us to estimate reduced lithium ion hopping rates at the surface. So this is again, work should come out soon. That was another example of how we can actually do like quantitative studies and learn something about the dynamics of a system. In this case, about the lithium hopping at the surface of this solid state electrolyte. And again, then in the future, of course, we sort of hope to actually study batteries like in a working environment in operando with an electrode on to actually study a functional interface. Okay, I have I think 3 minutes left. Since there's also a good number of ultra-fast folks around here and high harmonic people, I would guess. So I want to give another quick highlight here of works that we have done, and that is also my background in research is not just free electron laser research, but I am actually did for the most part of my career high harmonic generation and really ultra-fast attosecond science. So that naturally drew me to the idea of like, can we actually get rid of the need for an FEL to do these measurements? Can we do tabletop SHG? And so that was something that I was thinking about for a while already. And so then one opportunity came up when I talked to some folks in Paris at LOA, because they have quite a special source. So they have high harmonic seeded soft X-ray laser. I know in this lecture series, there's been a few talks already that talked about aspects of high harmonic and generation and strong field processes. So I don't want to explain too much about it, but basically what they build is a machine that has a conventional gas phase high harmonic source using argon. So they basically have to focus a titanium sapphire beam in a gas cell, generate high harmonic frequency, come all the way through the XUV. And then they have basically a plasma amplifier. The plasma amplifier is a gas jet where they come in with a Joule class laser to generate a highly ionized plasma. So they fire a Joule of energy into krypton, which then is ionized to the level of, I think, krypton 8+, where krypton and it goes into a electronic configuration of nickel where it has a metastable state that is then pumped with another infrared pump pulse. So they basically generate a population inversion in krypton 8+ in this jet, and that happens to be at around 30 electron volts. And essentially you can use then the high harmonic source to seed this atomic transition. And this is then essentially becoming an amplifier. So you have a high harmonic source with, say, an amplifier of a factor of, I guess, 1000 or something like that afterwards. And so they built this machine. Here are the pulse parameters. So they get XUV pulses with hundreds of 100 nanojoules, something like that. And then we went and said, okay, let's focus this as tight as we can. So we use a ellipsoidal mirror. We achieve a focal spot size at a range of 4 micron, and we focus it on titanium. So we put in a titanium foil. The energetics now look like this. We have 2 photons going resonant with the 3D states in titanium. And we look for the second harmonic now at twice this photon energy. And indeed, we can show that we observe it. So these are the raw spectra. I will admit that the spectrometer was not very well aligned for some geometric constraints. That's why these spectral lines are very much broadened out. In reality, these 2 features are actually very narrow band, like a few tens of milli-eV. So this doesn't really limit the interpretation, since we still have 2 separate humps that we can essentially integrate and look at the statistics. And that's what we really cared about, is to see the second order response. So here we plot now the square of the inbound intensity, and here we plot the second harmonic response. We see, in case we plot this squared over linear, it gives us a linear response, so it's actually quadratic. And that was the first demonstration that we did, that indeed with tabletop sources, I mean, this is still a fairly big laser system, but it's not unconceivable to reach, at least tens of nanojoules with pretty power with conventional high harmonic sources alone. Yeah, and then focusing down to 4 micron is also actually not too hard to achieve in a lab setting. So I'm expecting that there in the future will be more opportunities and possibilities to actually do second harmonic spectroscopy in a tabletop setting. With that, I would like to summarize. So I showed you, introduced you to XUV and soft X-ray second harmonic generation as a novel tool. In the novel ultrafast tool that allows element-specific probing of surfaces, interfaces, and also anisotropies in bulk. I walked you through one of our works where we studied the lithium displacement in polar metal, lithium-osmate, and I also showed you our most recent results on studying the surface of a lithium-ion conductor. Done at most of the works in lithium KH, and I also showed you that indeed there is prospect to generate second harmonics in a tabletop environment. With that, I like to thank you again for your attention, and also thank you once more for the invitation to this very nice seminar series. And of course, I'm also again grateful for all the collaborators, and we'll hand it back to Mike. Thank you.
All right, thank you, Michael, for the very nice talk. This is really exciting work. So there aren't questions yet in the Q&A, so I'll get us started. But if there's questions in the audience, please go ahead and type them into the Q&A. So my question is about the lithium osmium sample. In this case, you actually have broken inversion symmetry in the material itself. And so my question is about how, in that kind of situation, to what extent, or if at all, can you disentangle what's happening at the interface versus what's happening in the bulk? Are you sensitive to dynamics only at the surface or also in the bulk?
That's a very good question. I mean, if you have an inversion symmetry probing bulk, I would say this will definitely dominate your signal. I mean, you always have surface contributions, right? This is much like if you would do an optical laser experiment, right? But in the case you have a symmetry probing bulk, I don't see that you have any chance to isolate the surface in this case, right? I mean, the signal will be dominated by your bulk response in that case. So
in this case, if you were to excite some kind of a time-dependent structural phase transition where it goes from a symmetric to an asymmetric state, then you might expect that the you see more more of the surface when it's in the symmetric state, and then as symmetry breaks, you would see more of the bulk.
Yeah,
Okay,
yes,
that's interesting.
and actually, yes, and we see that in the experiment. Actually, it's in if you look in the, I think it's in the SI, we actually also have this we didn't see anything. So the thing is, we to make sure that this is actually coming from the phase transition, what we did in the experiments is to measure first at room temperature, and then while we cool down the sample, we looked at the second harmonic. And actually, once you go through the phase transition, you actually see the second harmonic popping up. So this was also an affirmation for us. Well, this is really the bulk state, comes from the symmetry breaking. And we did not see any second harmonic when it was in the symmetry state. I mean, this doesn't mean you can't probe the surface. It's just a matter of then you have to hit it harder. And I should say the crystal was a 1 millimeter spec that we had. So we were very nervous not to fry it. We had one crystal, that was it. I know we had two crystals, but they were like 1 millimeter, and dealing with osmium is apparently, I mean, I'm not a synthesist, but the folks who make those crystals, they were quite nervous about making those. This is not an easy thing, and it's, I think, hazardous and stuff. So we were quite nervous about frying the crystals. So, but I'm pretty certain that if you would hit it a bit harder, you would see surface response. And that's typically also, I would say, across these experiments I showed, it has always been the case. If we study a surface or an interface, we have to hit it actually quite hard. We have to increase the power of the FEL, go very close to the damage threshold, whereas if we are measuring bulk anisotropies, we can be a little bit more relaxed because we just get much more photons from the emission events.
I see.
So I would say for the lithium-osmate, for example, this was a large area sample. There we just, basically dialed up the FEL until we started to see damage, dialed it back a notch, and that's how we could do the lithium, the LLTO measurements on the electrolyte, because that was an expanded large area sample, whereas the lithium-osmate was a teeny tiny crystal, so there were some constraints there.
All right, we have another question this one's from Jonathan. So in the LLTO data, the SHG spectra look a lot cleaner than in, I think, any of the other samples. Is this something different about the light source or the sample or something else?
Yeah, Jonathan, good question. I would say that it's a matter of statistics. In case of lithium-osmate as compared to the LLTO, I think we have a difference of an order of magnitude of data points. That was just, beam times, how they work. It's like you set stuff up, then stuff breaks, stuff doesn't work, and you have like 3 days. And then I think in the case of LLTO, we just had more time where it just worked. So we could accumulate longer for the data points. And it's as simple as that. So it's a matter of statistics to get clean spectra. It's, by the way, also one thing where we're excited about, for example, the upgrade of LCLS here in Stanford, where going to megahertz rates as opposed to the current kilohertz rates of FELs, or even hertz rates like Fermi runs at, or currently LCLS runs at 120 hertz. That's like one of these improvements going to megahertz rates like LCLS2. This is going to be a total game changer for this type of spectroscopy, as long as the detectors are fast enough, say. You can get order of magnitude higher statistics, and we would expect that you can get very detailed and high quality spectra this way, and probably then can do things like polarimetry, and you can do time resolved. And right now, I mean, I would say with those measurements I showed, like each of these measurements is a whole beam time. So it's like 3-4 days, 24/7. That's about as much as you get as currently one spectrum. And I would anticipate that either with tabletop availabilities or higher rep rate FELs, as we have them coming up, you will be able to actually then do time-dependent tracking of these features. And it's really a unique technique in a way what observables you get. There's you don't have much other techniques that can do these certain types of specificities. So I think especially charge transfer dynamics at buried interfaces, this will be quite interesting to study.
So with a megahertz FEL, do you worry about thermal effects?
Well,
at that point,
it's of course a good question. I mean, of course you worry about thermal effects. The thing is, if you are at these high rep rates, you can probably dial away from the damage threshold quite a bit, because if you get 1 photon per shot, it's still much more than if you would be hitting it near the damage threshold to get something out in a reasonable time with a 100 hertz machine, right? So it's it's a trade-off. I mean, I would still expect that also, you may have a cryostat, so you can dump some heat there, and I think there are some ways to still take good data. I should also say the other thing we were quite interested in, I haven't shown it, this is all work that's underway is that we look at, since, I mean, we're working on chemistry, so we're also interested in liquid interfaces, for example. So we're, doing experiments where we look at liquid surfaces, liquid interfaces, and things like that. So in those cases, when you have refreshing samples, then, damage doesn't even matter at all. So. Yeah.
All right, well, I think that is it for the questions now, and we're at 4:10, so I think it's probably a good chance to start the after session. So as usual, after the session, we have a time for a short Q&A with the speaker for students and postdocs. I have posted the Zoom link in the chat, and so before you sign off, Michael, I just want to take a second to just say thank you again for such a great talk. This was a really nice talk with some very exciting results. Jonathan, am I correct that this is the last talk for this spring
This is
session?
the final talk of this season. Yep.
All right, so this is the final talk of this season, and we look forward to restarting this again probably in the fall. And thank you all for attending, and thank you, Michael, for the great talk.
Thanks for having me. We'll switch to the other room then. Thank you again, and see you soon in Orlando. Bye.
Yep, bye.
Bye. I'll stop the streaming. All right, the YouTube is off.